yo, ella fue la que me dijo, lo que usted dice, ahorita miro, ahorita le preguntamos a ti. Yo digo, bueno, claro, lo que usted dice tiene sentido. Coman y que vuelvan.
Bueno, gracias por haber venido al seminario de Jorge. Todos sabemos que había paella gratis ahí fuera y estáis vosotros aquí, o sea, no os habéis enterado. Lo digo porque falta la mitad del instituto o más, ¿no? Pero bueno. ¿El Consejo Interno? No, pues entonces sí, pues la intersección es nula. Bueno, entonces Jorge Barrera es un colaborador de hace ya bastante tiempo y amigo. Hizo la tesis doctoral en el IAC con Begoña García y Jesús Falcón Barroso como cosupervisores. Anteriormente hizo la maestría en Bonn de año 2008 al 2011, o sea que tiene ya un bastante bagaje astronómico. Y una vez que terminó la tesis doctoral pidió una beca postdoctoral aquí y no se la dieron. Pero eso es porque somos mejores que la John Hopkins, porque allí sí se la dieron, y entonces está de postdoc en la John Hopkins, lo cual hace ver el nivel que tenemos en la UNAM. Rechazamos gente que admiten en la John Hopkins. Eso está bien, ¿no? Y bueno, ahora está de vez en cuando. Yo vino hace 2 años, dio un DAEC, creo, y hemos seguido trabajando juntos y bueno, evolucionó de califa a manga, como casi todos los estudiantes, que ya nos hemos quedado sin estudiantes en califa por evolución como los Pokémon, y ahora es postdoc. Y no, él es colombiano. Perdón, sí, es paisa. Sí.
De hecho, creo que alcanzamos a tomar clases juntas, las últimas clases de pregrado, en el 2008, 2007.
Bueno, y sin más, que hable él, que es el que tiene que hablar hoy.
So I'm gonna give the talk in English. I hope that's okay. Well, you have questions anyway, you can ask me in Spanish. So first of all, I want to thank you, all of you, for being here. Also, I want to thank all the people that have been involved that I met today, or in the last week since arrived here in Mexico. The science that you are doing here is very exciting. The work that you are doing here is really nice. So I'm really glad that I can share my result with you, and I can know what you are doing here at UNAM. So for that, I'm really glad. And today's talk, I will show you the result that we have, the work that we have carried on in Hopkins with my supervisor, Steen Hegman, postdoc, Wantun Shu, and Nadia Sakanska. And of course, the data that we are using is based on the analysis that has provided by Sebastian. So before I show you the results, I would like to introduce you to what we know about metallicities. The work is about metallicities, the mass-metallicity relation. So I want to show you what we know about metallicities in these galaxies, so late-type galaxies, prior to the MaNGA or the IFU era. Then I will show you what is MaNGA survey. Most of you have some idea what MaNGA is, but I would like to give you an overview of this. Then I will present the results, what is the actual spatially resolved mass-metallicity relation, what is the impact of the host properties in this relation, and finally, I will try to show you some ideas that we have, some very basic ideas that we want to use in order to understand why we are having this local relation, the physical scenario. So let's start with this plot. This is for the people who is working in extragalactic astronomy, I think this is one of the most familiar plots that you always see even in the textbooks. This is called the global mass-metallicity relation, and global is quoted for a reason that I will explain to you later. So what we have basically here is that in the y-axis you have the metallicity derived from the ionized gas. In the x-axis what you have is the total stellar mass. And the first thing that you can notice here is the relation that they follow. So as the mass increase, the metallicity also increase and reach this like a constant value here. You also notice that this is a very tight relation. First of all, I mean, there are like 500,000 points here, so each of these points represent one galaxy. So you have a lot of galaxies here, and you also notice that the relation is really tight. So you see a really small scatter with respect to this red line, which is plotted here. This is the standard or the distribution of the residuals with respect to this line. So this is a really nice relation to use, but what is it telling you? So I want you to keep with this, to bear these 2 points. The first one is that this has been used in order to understand the evolution of galaxies. A lot of scenarios have been proposed in order to understand this. A lot of physical scenarios in galaxy evolution has been proposed to understand this relation. And the other thing that I want you to keep in mind is that this relation that you are having here, the way that it's derived is a little bit tricky, in the sense that what you have in the x-axis here is some quantity that you derive using photometry. Whereas the y-axis, what you have here, the metallicity, is a value, is a quantity that observationally you obtain from a single aperture, from a spectroscopy from a single aperture. So you are only having information from the central region of all of these galaxies. So that's something I want you to keep in mind, because we will use this later for the discussion. The other thing that we know for metallicities is the distribution. So with the surveys, IP surveys, for example, Khalifa, we know that the metals, the distribution of the metal, the radial distribution of the metals in late-type galaxies. In particular, I want to highlight this study from Sebastian using Khalifa data. And he and his collaborators, they realized that if you use, or if you plot the radial distribution of the metals using a particular scale, the effective radius, and you scale with respect to the mass, the gradients or the distribution that you see with respect to the radius is really, really similar. So no matter the mass that you have, no matter the morphology that you could have, this distribution is very, very similar. So I also want to keep you this in mind. So we have how the global mass metallicity is, and how the gradients, or how the metals distribute in these galaxies. Yes, this is for late type. That's why disk, or late type galaxies. Thanks. So now I want to show you what is the MaNGA survey. I guess most of the people that are here are aware of that UNAM is part of the MaNGA survey, or the Sloan 4 survey. And in particular, the people who is working in extragalactic astronomy is aware of this, that UNAM is involved of this. Nevertheless, I would like to give you some idea for those who doesn't know what is the MaNGA survey. So basically, the idea of MaNGA survey, first of all, that stands for Mapping Nearby Galaxies at the APO. The idea is that we will observe around 10,000 galaxies in 6 years with a median redshift of 0.03. The idea also is that the distribution of this galaxy that we will observe is flat in this regime. And we will cover, or we want to cover the galaxy, a big chunk of the galaxy, so or the objects. So all of the galaxies, all the sample will be at least covered by 1.5 effective radius, and a representative sample of these galaxies will be covered up to 2.5 effective radius. And this is the, the distribution that you will have, that we are having for this sample. So you have a primary sample here that spans a wide range in luminosity, so stellar mass, and here you have the redshift. So you have the primary sample here and the secondary sample here. So how do we observe? So basically what you have is bundles of fibers, like the one that I'm showing here. So each of these fibers is connected to one spectrograph, a Bose spectrograph. And the idea is that the light that comes from each of these fibers will go and will be scattered, and you will have the spectra here at this wavelength regime. So for each of the points, each of the region that you will have in each of the galaxies, you will have a spectral information. For all of these fibers, you will have a spectral information. So after reducing, observing and reducing the observation, what you have is a data cube. So what is a data cube looks like? So this is how a data cube looks like. The idea is that you will have, for the x and the y axis will be the projection in the sky of your object or your galaxy. And in the z axis, what you will have is the wavelength. So just to give you an idea, each of these points that you will have here will correspond to one of these spectra, so the black spectrum or spectrum. And as I told you, we are, I forgot to mention. Usually I try to, when I give this talk in other institute, not Sloan Institute, I always remind the people that this data is available to the public. But here, since we are in a Sloan Institute, I want to remind you that you have a lot of data, which is more data than we have here. MaNGA is already observing, 3,000 galaxies by now, around 3,000 galaxies. And you have the data here. Not only that, you have the analysis done by Sebastian here, and I will come to this in a moment. So you are in a really, really good spot right now. So as I was saying, you have like 3,000, 1,000 galaxies, and in each of these galaxies you have, for a given position, you have one of these spectra, so it's a lot of information. And if you want to extract physical information from this spectra, you will require to have what we call analysis pipeline, an IFU analysis pipeline. In this case, for this study, we are using the pipeline developed by Sebastian Sanchez and his collaborators here at UNAM. So the basic idea is that for each spectra, you make some fitting, you have some fitting of the continuum using single stellar spectra, single stellar population spectra. Then you have you can also fit the emission lines, which will give you information about the flux or the properties of the emission lines of the ionized gas. For example, the flux, the standard, the equivalent width, the full width at alpha maximum. So all this information, you can extract that for each of the points, and then you can build maps out of that. So how does maps look like? So this is an example. So what I show you here is a Sloan image of this given galaxy. And in this map, what you have is the surface mass density. So this is the stars or the mass of the stars that you have for each of the spaxels, each of the points that I was mentioning before. And then you can extract also more information. For example, the flux for any emission line that you want. For example, here I'm plotting the H alpha, H beta, nitrogen 2, and oxygen 3. So as I said, we have all this information for all these sample of galaxies. We want to be a little bit constrained. We want to constrain the sample that we have. We want to have, as we were saying, later galaxies, or these galaxies. So we make a very simple cut in our sample to have to be sure that we have these galaxies. This leaves us with 653 these galaxies. But we want to constrain this a little bit more because we want to, in order to obtain all these properties that I will show you later, we need to be sure that these are derived from star-forming regions or star-forming spaxels. So in order to do that, we have making a selection using the BPT diagram. The BPT diagram is basically just a diagnostic diagram where you put the flux ratios here. So in the y-axis, you have the oxygen 3 over H beta. In the x-axis, you have nitrogen 2 over H alpha. And you compare depending on where these ratios are in this diagram. You can say either if this is, you have some idea if it's a star forming, if it's here, if it's composite, as some people call it, it'll be here, or if it's something else, it will be out of this region. So as I said, in order to be sure that we have star-forming spaxels, we select those spaxels to be here in this region, so to be star-forming spaxels in this diagram, but we also constrain a little bit more, and we impose that the equivalent width of H alpha to be larger than 6 angstroms. So this is this cut here is represented by this histogram here, so we are sure that we are taking spaxels that are indeed star-forming spaxels. Then after we make this selection, this cut, we can also use all the machinery that has been developed in order to understand, or in order to have some idea of the metallicity using calibrators. So in this particular case, we're using the Rafaela Marino collaborators calibrator, which is oxygen 3, which is this, and nitrogen 2, which is this. So with this, we have all the information that we want. So what is MaNGA bringing to the table? So the first thing is that we have a spatially resolved information. We have the chance to study how the metallicity is related to the mass content in each of the points, in each of the regions of these galaxies. Moreover, since we have integral field spectroscopy, we can ask ourselves, what is the distribution of these metals? And the third part, which I think is the most important property that MaNGA has, is the statistical power that it has. So this is the first time that we have spatially resolved information for such a large sample of galaxies. We are covering a wide range of properties, like stellar mass, like star formation, and this could be done only with MaNGA. So with no further ado, this is the MaNGA sigma metallicity relation. So in the x-axis, what you have instead of the total mass is the surface mass density. In the y-axis, what you have is the metallicity derived for each of the spaxels. So I want you to remind this, I want to stress this out, is that now we are having a metallicity and the stellar content or the stellar mass for each of the points of these galaxies. It's no longer the metallicity for a central region or for an integrated region. This is the metallicity for all the spaxels where we consider as a star forming in all these galaxies. So here we have around 500,000 of spaxels. And you can notice also how this relation is so similar as the one that we were observing before for the global properties. This is something that, for me at least, is very, very striking because it's the relation is very similar and it covers a wide range of surface mass densities. The other thing that you notice is also the scatter. The scatter is also really small as the relation that was presented before for global properties. So you can say, well, how this relate with the size, the sample size? In other words, how can we compare this with different surveys? So we have done this. What I show you here is the comparison of, or the relation that we derived here in the contours with two previous HIFU surveys. This line is for pink survey, which is presented, the PI is Fabian Rosales, who is a researcher at INAOE here in Mexico. This is the relation presented by the Khalifa survey, which is Sebastian is the PI, and this is the relation presented by MaNGA. So as you can see here, and of course, the sample size of this is very different, almost an order of 10 difference. So pinks is around, I don't know, 40 galaxies, 40 these galaxies, or 30. Whereas Khalifa, for this particular study, is 150 galaxies. And here we are presenting 653 galaxies. So you can see there is almost an order of magnitude for each of the surveys. And when you study this, so again, it's remarkable that even if you have a low number of galaxies or 600 galaxies, this relation, spatially resolved talking, is very, very similar. So this is something also remarkable. But we can go further. As I said before, we have 653 galaxies that cover a wide range of global properties. So one other thing that that people usually ask when you want to study how one parameter, let's say an external parameter, is affecting a relation is by studying the scatter of this relation. So for example, the scatter that I showed in the previous relation, on the global mass-metallicity relation, you can study how much the scatter, or let's say the deviation of this point with respect to this best fit line, change with respect to this external parameter that you want to study. So this is something that we did. We did with the mass. So what I showed you here is the residuals of this local mass-metallicity relation with respect to global properties. So in the y-axis is this scatter. In the x-axis, what you have in the top is the total stellar mass. And in the bottom, you have the specific star formation rate, the global one. So what you see, the first thing that you notice is you have quite a scatter cloud here for all the spaxels that you have, also here. But once you start to measure these properties at beams of total stellar mass or specific star formation rate, you start to notice that the mean values of these beams are really close to 0 for a wide range of global properties, like the total stellar mass or the specific star formation rate. So this is very remarkable. This is very remarkable because we are seeing that for a wide range of global properties, if you go to really low the total stellar mass or low mass galaxies, you start to see some difference. Or conversely, if you go to higher star formation rate, you start to see some difference. But for the big majority of the big chunk of galaxies that we have, this relation is almost independent of the total stellar mass. So as I said, this is one of the biggest, I think one of the biggest accomplishments that MaNGA is bringing to the community. But we can also, study this in a different way. As I said before in the introduction, we can study how the metals, distribute in the galaxies. And we ask ourselves, okay, can we reproduce, or can we build this distribution that we are observing of the metals using the relation that we have, this sigma metallicity relation? So in order to do that, we built, or what I show you here is the plot of the surface mass density profiles divided by different total stellar masses, right? And then we compare, or we subtract the best, or the metallicity gradient using this and the relation that I just saw before, and we compare with the one that we are actually observing. So this is the difference, So again, this is the difference between the metal gradient that we build using this and the one that we are actually observing. And what you have again is that for a wide range of total stellar masses from 9.2 to 11, so this is almost 2 orders of magnitude, the gradients are very similar to each other. So the difference is almost close to 0. Regardless, the total stellar mass or the median values are really close to 0. Again, if you go to lower masses, then you start to see some deviation from this relation. But in general terms, the gradients that you are observing or the distribution of the metal that you're observing can be explained by the properties, by the distribution of the mass that you are seeing. So this is telling you that whatever is happening seems to be happening in local scales rather than global scales. So this is something that I want you to keep. This is, for me, one of the main points of this talk or this work. First of all, yes, we find a tight relation of these two properties, something that we have seen before in different IFU observation or IFU surveys. Secondly, we find a weak dependence of the residual with respect to this global parameter, like the total stellar mass or the specific star formation rate. And as I showed you before, with these two information, the density, the stellar density or the distribution of the stars, and this relation, we're able to build the distribution of the metals. And as I was saying before, this is telling you that whatever is happening, whatever is enriching the material, the ISM, seems to be happening locally rather than globally. So the process that we are observing seems to be happening at a local scale within the galaxies rather than some external parameters. So the second part of the talk that I want to show you is, while we have tried to come up some basic, let's call it like a toy model, in order to explain what we are seeing in this with the MaNGA observations. So we came up with this very simple local leaky box model that I want to explain to you in a while. So the first thing that we did is to assume that this galaxy looks like this. So yes, like an onion. Why? Because we want to assume that we have the mass is distributed in an inside-out fashion. So we have, or the growth of the mass is an inside-out fashion, and this idea has been come like 40 years already. We also want to assume that the gas, there is a constant accretion of pristine or cold gas toward the galaxy, but it's smooth. And we also want to assume that the density of all the material, all the baryonic mass that you have in a given radius, since is constant, and is the first mass that you acquire when you get this smooth accretion. So in other words, no matter how the density evolves, if it's transferred to stars, it is kept to the gas, or if it's spelled out, all the density that you have evolving with time will be the same as you have at the beginning. So with these very simple assumptions, you can also use very prescription of the evolution of galaxies, like the Kenik-Schmidt law, like the outflow rate, and then you can build some, or you have some idea of what is the evolution of the gas density. With this, you can also make some assumption of or you can build what will be the chemical evolution of the gas. And if you transport this, you print this out, or translate to the parameter that you will have observationally, like the star formation rate density and the stellar mass density, something that we had before, we can compare the metallicity that we have, the observed metallicity, with the metallicity that you will derive using your models. So we have done this. We are assuming that here, so there is no global outflow. There may be some material that is leaving the this onion ring, but if you sum it up, what you have in the end should be the total, should be the first density that you put. Yeah, but this is the inflow. This is accretion that happened at the beginning of the time.
At the beginning only.
Yes.
It doesn't continue.
No, exactly. Then keeps evolving. This only have a single density that is evolving locally.
Then now you have I don't understand if the galaxy how can it always evolve.
No, but I'm saying it's constant. The first density that you have is constant. Yeah, I don't mind. So yeah. So well, with this very simple model, what we did was to plot. So once again, we have the same plot that I showed you before, the surface mass density relation, but now we have segregated our sample with respect to the specific star formation rate in these 3 different bins. So red is for low star formation rate, and blue is for high star formation rate in each of the spaxels. And once you have these, and you use the new reparameterization that I just showed to you before, namely basically the Koenig and Schmidt law and the surface mass density, weighted by this loading factor, you will have you will see how this relation change, and at least the scatter that you have, it's heavily reduced. So in other words, what you have in here is that the metal content of this spaxel seems to be more related to the fraction of gas that you have in the spaxels rather than the surface mass density. We tried to do some more tests. As I said before, as we are discussing before, the main parameter that characterize these densities, this surface mass density in the stellar component and the gas component, is the initial one. So you can ask yourself how much it changed if you study different initial sigmas, different surface mass densities, how they might change this parameter. So this is just the dashed line represent this line here, and then you can see what the model seems to telling you is that for a different surface mass densities, for a different spaxels, you'll have an initial surface mass density, and it will evolve as higher, for higher densities. So as I said again, this is a very toy model. So from this leaky box model, we have some idea of what is the localizity of the properties. That this is that once you have an initial surface mass density for a given radius, this fully describes the evolution of the local properties. We also seen that the gas fraction is an important factor, more than even the surface mass density of the stellar component. And there is also, as I just showed in the previous plot, if you can constrain the density, if this model holds, and if you can constrain the density, the initial density for cosmological times, then you may constrain the whole properties of the galaxy and its evolution, so which is a really cool thing to do. And as again, this is a very toy model in the sense that, as we are just discussing, we do not consider like the impact of global properties. We are not considered as outflows, at least like global outflows or stream outflows. We are not considering, for example, that there may be some, there is some migration, radial migration in the galaxy. So you need to consider that, and you need to see how much this may affect the metallicity and how it's compared with the observations. So I leave you with this, and thank you very much.
Questions, comments for the speaker, or suggestions?
Very interesting presentation. I mean, when you said that the gas fraction is an important factor, that reminds me of Tinsley's contribution, where she found that in her models and in the data. What's that different from your models at the end, from the closed box model? To a first order, you still have a closed box model, right?
Yeah.
There's no migration.
Yeah.
There's no infall. And therefore, it would not solve the problem of the distribution of the G stars metallicity, no?
Yeah, but yeah, I mean, I guess I also have to clarify that when you say leaky box model, is that a fraction of the gas that is is expelled by supernovas could either remain or could leave, and I guess that's the fraction that we need to. That's why it's called leaky box model. That is the fraction that we need to acquire to be sure of, in order to to be this model to be true. So it's not exactly as a closed ball model, because as we have seen before, a closed ball model is not very well representative. Gives you a broad idea, but it's not well representative. And these models try to account for this little fact that you have some material returning to the ISM. But yeah, I mean, maybe it's an oversimplification.
I have a question, sorry, regarding the metallicity differentials. Why is that at lower stellar masses you deviate from zero?
Thank you. So yeah, this is something that we do see. You mean that one, right? Yeah. We do think that for low mass galaxies, there should be some I think, maybe I'm wrong, but I think that for low mass galaxies, the gas fraction is higher. And when the gas fraction, and you can see in papers and articles that do observe that, or they observe 80, 90% the gas fraction. So when you do have that, we do think that, of course, the metallicity will be lower. But this is happening only for the low mass, yeah. So I think it's for a higher, this because of you have a higher gas fraction, yeah.
Jorge, I am quite confused about the conclusions that the metallicity should depend only on local properties. I think it's very clear that the mass is the global mass is a very important process in the evolution of the galaxies, in the sense that low massive galaxies are delayed in their star formation. This is why they are less metal. So how to concile these two local and global
I think
effects?
we need to shift a little bit the idea of how we are observing galaxies. I think that we are observing galaxies, so we were taught that the only way that we can observe galaxies is at data points, right? So a galaxy is only allowed to be one mass, one star formation, and one metallicity, period. But now we are observing the IFU data that we have a wide range of properties that is happening at different parts of the galaxy. So this is something that I don't show here, maybe. Yeah. So this is the actual, the contours. This is another representation of the plot that I showed before. And what this plot is telling you is that you could have spaxels, in a given galaxy with a given mass. For example, low mass galaxies could have the same metallicity as spaxels, which are located in a higher total stellar mass. So this is what we're trying to do here, is trying to shift the concept of galaxies to be just points. They may be cows, like round-shaped cows, but they have a lot of properties inside the galaxies, and that's something that we try to make the shift of gears in the understanding of evolution of properties.
The local relations are the key ones, but you have massive galaxies on average are denser, have higher surface brightness typically, and this is why they lie in the global relation, in the more metallicity, and smaller galaxies are less dense, they have smaller surface densities. So this is probably the connection between one and other is because the surface density depends on mass at the end, no?
No.
Yeah, no, but it's the other way around. The more massive galaxies are more massive because they have denser areas. And there is a local downsizing also, so that this fact that the evolution happens is simply that the ones that are more massive have evolved faster in the inner part, and then in the outer part. Is the local properties basically what dominate the baryonic thing. I'm not talking about the dark matter, but the evolution of stellar evolution. And you know that because this is one of the results of Hector article. So the inside-out downsizing that we have found. But I just want to make a note in here. Sorry, I cannot regret from making a note. or retain for making a node. When you make, when you were talking about the statistics of using different surveys, you may recall the point statistic is actually larger in the case of pings than in the case of Khalifa, and it's the other way around, because the number of points you're sampling with MaNGA is lower. So if you go to local relations, you are showing a relation with 500,000 points. At the end of MaNGA, you will have a relation of the order of 5 times more. But in the case of Khalifa, we already have that, because you have more points. So since the statistic is the same, it doesn't matter if the relation is the same galaxy per galaxy, it's not surprising that you find exactly the same kind of relation that we have found before.
Yeah, that was the point.
Just the point. If you just sample 3 galaxies of different mass with μ's, you get exactly the same relation with the same statistics.
Exactly.
It's just if you change galaxy by galaxy, where you see it different. That's all.
Well, I find this is a change in paradigm, your interpretation of that relating the spatial distribution. Well, it's interesting that the 3 samples you showed, Khalifa was closest to MaNGA than the intermediate size sample, right? In the curve, the 3 curves.
Yeah.
Yet the pings has an intermediate number of objects. So it's interesting that Khalifa, having less object, is closer to MaNGA, which has the highest number of sample galaxies, right?
The number of points
So in pinks you have H2 regions, right?
I want to understand, you are very young, of course, but it is too much to say that before galaxies were looked as 1.1 cow. No. There has always been 2D and long slit. Sorry. Now, my question is the following. What I don't really understand, 2D, there's always been. Of course, CFUs, I understand very well, are much more efficient. But 2D has been there always. Okay, now my question is, what is the benefit of 3D? Because to me, 3D means dynamics, and so I don't understand.
So, regards the first point that you mentioned, when we talk about, consider galaxies as points, I'm talking about statistically speaking. So before, when I said this, you didn't have, yes, of course, from the 70s you have long slit spectra from later galaxies, of course. And even this, you have from the 70s and from the 80s, you have gradients of the metal content of galaxies. But statistically speaking, this was the first time you have a large sample of galaxies covering a wide range, almost 3 orders of magnitude of stellar mass, when you can say something, statistically speaking, of galaxies. So that's, that's what I'm saying, that treating galaxies as a point. That was the first thing. The second thing, I didn't understand what you were saying. So what do you mean by 3D? Yes.
Yeah.
Well, this is just a way to represent, the way we represent the observations. Just saying that for each point, x, y, meaning the projection in the sky, you have a spectrum. That's your third direction. You are right, that could be a little bit misleading. Nevertheless, you can have 3D information from the velocity fields. That's true.
That's my point.
Yes, exactly. So, yeah.
Okay, let's thank the speaker again.
Thank you.
All of you are in Spanish. No. Bueno, hasta aquí se termina ya el coloquio, ¿sí? La situación es que una persona va a presentar un video el cual viene de parte de Débora. En este video tuvo algunos premios y muchas personas de este instituto, ¿de cómo? México Tierra de Astrónomos. En este video aparecen algunas personas del instituto y a petición, muchas personas le han dicho a Débora que lo quiera proyectar. Él dura 20 minutos, entonces hay una lección. Vamos por el after party, comemos y lo traemos, continuamos viendo el video, o quien quiera, o de una vez esa lección. Entonces
el ILCE y ACISEC, y bueno, y algunos de los comentarios que recibí del público cuando lo exhibieron en los cines del Centro Cultural, que me emocionó, fue de una señora ya de 80 años y me dijo, si yo hubiera visto este documental cuando era joven, hubiera sido astrónoma, ¿no? Y otra de las, pues este documental, bueno, eso es todo, ¿no? Bueno. Ok, gracias.
México, tierra de astrónomos.
La astronomía es parte de la cultura. Nosotros necesitamos que en nuestro país la cultura se desarrolle y por lo tanto que se desarrollen todas las ciencias, todas las artes, todas las humanidades, todo lo que hace el hombre. Y en ese sentido, la astronomía es una parte fundamental de la cultura también. La primera conexión a Internet en México se hizo en el Instituto de Astronomía, en fin, podríamos seguirnos por ahí. Hay otro aspecto. La óptica profesional surge en México en el Instituto de Astronomía en finales de los 50, principios de los 60. Había 3 compañeros que se dedicaban a la óptica en el Instituto de Astronomía para hacer instrumentos de los astrónomos, espectrógrafos, telescopios, cámaras, en fin, todo este tipo de cosas. O sea, el desarrollo de la óptica en México empieza por necesidad de los astrónomos en el Instituto de Astronomía.
Estudié astronomía de casualidad, como tantas cosas que pasan en la vida. A mí me gustaban las matemáticas. Iba a un colegio francés y siempre saqué 0 en francés y 10 en matemáticas. Así es que sabía que lo mío eran las matemáticas.
Cuando terminé la preparatoria no tenía ya una vocación. Me gustaba la historia, las ciencias políticas, la ingeniería petrolera, leer y un poco las matemáticas también.
Francamente, no sé, yo nací con ese gen y desde que tengo uso de razón, e incluso mi mamá me recuerda que yo decía que yo de grande iba a ser estrellífera.
Bueno, desde muy pequeño tuve yo inquietud, mucha curiosidad por la naturaleza, y viendo el cielo en las noches despejadas allá de mi sur, en el sur de Bolivia, pues siempre quedaba fascinado, ¿no?, por esos misterios que en ese momento creía encerraba el firmamento.
Precisamente en 1994, que venía un cometa, iba a pasar cerca, incluso tan cerca que se desvió por un jalón gravitatorio de Júpiter y se iba a estrellar con Júpiter en 1994, el cometa Shoemaker. Y bueno, como yo en aquella época era estudiante y no tenía dinero para comprarme un buen telescopio, pues al final, junto con un primo, nos pusimos a fabricar un telescopio, aprendimos, y bueno, al final lo que fue pasando es que de las primeras cosas que entendí la física que me gustaron, porque entendí, fue precisamente cómo se movía la Tierra alrededor del Sol y cómo se definía la Semana Santa, que para todos los niños es muy importante porque son las vacaciones. Entonces, cuando entendí que las vacaciones las definían a partir de la luna llena y entendí por qué existía o se veía la luna llena, pues de alguna manera eso me marcó y finalmente, bueno, acabé haciendo astronomía, física y diseño mecánico para telescopios.
Y un día en la madrugada mi papá me despertó para ver un cometa y me pareció maravilloso. Cuando mi mamá se murió yo tenía 13 años y mi hermana la mayor tenía 15 y me dijo, tú eres tontita, mejor estudia algo más práctico. Así es que estudié física. Y por fortuna, en la Facultad de Ciencias se había un anuncio equivocado que decía carrera de astrónomo. Tuve grandes maestros, Manuel Peinbert, con el que tengo el gusto de seguir colaborando.
Nos fuimos al Observatorio de Tonantzintla en Puebla a mediados de año, a mediados de los cursos, y ahí nos encontramos con el doctor Aro, pues desenfocados y sin idea de nada, y le dijimos, bueno, pues venimos a ayudar a los astrónomos, fue lo que se nos ocurrió decir. Íbamos sábados y domingos a Tonantzintla en Puebla, veíamos 3 o 4 placas y después de varios meses habíamos encontrado 100 objetos con líneas de emisión. Estos objetos resultaron ser nebulosas planetarias y pasó por ahí un astrónomo checo que estaba haciendo un catálogo de estos objetos, los metió a su catálogo y les puso nuestro nombre. Se llamaron y se llaman nebulosas planetarias Peinbert-Pattis del 1 al 10. Y al año siguiente me puse a trabajar con Rafael Costero en lo mismo y encontramos otras 14 que se llaman Peinbert-Costero. Entonces yo dije, bueno, pues si para esto lo único que necesita uno es trabajar un cierto número de horas al día y encuentra uno cosas que nunca nadie ha encontrado, esto me motivó muchísimo para dedicarme a la astronomía.
Y bueno, desde chico quería primero ser astronauta, luego ya en la adolescencia decidí definitivamente que quería estudiar las leyes físicas de la naturaleza, ya sea física de partículas elementales, el micromundo, ya sea astronomía, astrofísica, es decir, el macromundo. Y desde entonces pues me mantuve firme en esa curiosidad y en ese deseo de tener un entendimiento unificado de la naturaleza, del universo y de cómo evolucionan las cosas.
Pues bueno, como que en secundaria anduve preguntando y de alguna manera me enteré que había que estudiar física, que no había carrera de astronomía. Y la verdad es que yo en ese momento tenía una maestra de física en mi casa. Y cuando me dijeron hay que estudiar física, yo dije, guácala. Pero tenía un maestro de matemáticas maravilloso. Entonces pues ya me seguí en ciencia.
Sí, bueno, dificultades siempre las hay. En mi caso, siendo boliviano, era aún mucho más complicado. Al final de las opciones que tuve, decidí irme a lo que es la ex Unión Soviética, Rusia hoy día. Y bueno, luego las dificultades de aprender un idioma nuevo, el ruso, para poder estudiar y de esa manera logré seguir todo el camino académico que se requiere para llegar a ser doctor en astrofísica, ¿no?
Mira, afortunadamente una vez que empecé a trabajar en lo de las nebulosas planetarias, el doctor Aro me consiguió una plaza de ayudante de investigador, hice mi tesis de licenciatura y me fui al extranjero, a la Universidad de California, Berkeley, a estudiar el doctorado en astronomía. Tuve que aprender inglés, regresé a México y otra vez el doctor Aro logró que hubiera una plaza de investigador, competí y obtuve la plaza.
Bueno, las mujeres en general en el planeta tenemos dificultades enormes porque hay un prejuicio en contra de nosotras. Las religiones, por ejemplo, en su mayoría pues consideran que las mujeres son inferiores a los hombres. Además de que piensan que es bueno sufrir, o sea que estamos amoladas. Y efectivamente, cuando yo era pequeña, mi papá me dijo que mi cerebro pesaba menos que el de los hombres y por eso mi destino era quedarme en la casa a cuidar a mis hermanitos. Efectivamente, los cerebros de las mujeres pesan menos que los de los hombres, son más pequeños, pero no quiere decir que no podamos pensar y tener ideas novedosas.
¿Qué tan difícil es? ¿Es igual de difícil o fácil que cualquier otra área del conocimiento que te guste o que quieras hacer? Si te gustan los idiomas, si tienes facilidad, no se te va a complicar. Si te gusta el deporte y tienes una condición física, no se te va a complicar. Lo malo es cuando quieres ser deportista y tienes una condición física como el pie plano que dicen que algunos tenemos o tuvimos, y pues no puedes ser un gran deportista. Ahí lo que quiero decir es que es importante saber qué es lo que te gusta y si se puede estudiarlo o desarrollarlo, y al final pues no se te va a dificultar, simplemente lo vas a disfrutar.
Bueno, no fue muy difícil conseguirlo porque me gustaba mucho, y cuando uno hace lo que le gusta, pues todo se facilita. Mi familia me apoyó. Bueno, mi abuelito quería que me casara desde que tenía 16 años, pero mi abuelito era rabino pero no importa. Mi mamá me apoyó mucho, me apoyaron. Luego aquí no había posgrado y entonces apliqué a una universidad en Moscú y había becas y me dieron la beca.
La investigación que he realizado tiene que ver con la química que existe en el universo, desde que se formó hasta el presente. Para lograr esto he trabajado en las galaxias espirales. Resulta que en las galaxias espirales como esta, que tienen hermosos brazos, hay más estrellas en las partes centrales que en las orígenes. Es decir, la evolución estelar es más intensa en las partes internas de las galaxias que en las partes de afuera.
Y en un área en que hemos trabajado muy activamente es en determinar con qué composición química se forman las galaxias. El hidrógeno y el helio se forman durante los primeros 4 minutos que siguieron a la gran explosión, que es el empiezo de la evolución del universo observable. El universo observable empieza a una gran temperatura. Al segundo de iniciada la expansión tenía una temperatura de 15.000 millones de grados. A los 4 minutos su temperatura había bajado a 800 millones de grados. Y en ese intervalo se produjeron reacciones nucleares que nos dieron como resultado el 25% de helio y el 75% de hidrógeno por masa. Pues este resultado que nosotros hemos obtenido apoyan a la teoría de la gran explosión y es una restricción importante en el estudio de la cosmología y en el estudio de la formación de los elementos y de la formación de las estrellas y de la formación de las galaxias.
Resulta que para formar las galaxias es imprescindible la así llamada materia oscura. Es una componente invisible que hay en el universo, de hecho es mucho más abundante que la materia ordinaria, que la que forman los elementos químicos de las cuales estamos hechos nosotros, los planetas, las estrellas. En realidad en el universo hay mucha más materia que sabemos que está ahí por su gravedad, y a esa materia se la ha llamado materia oscura. Más bien para mí es materia invisible, es materia que no interactúa con la radiación electromagnética, con la luz, por eso no se puede ver, pero sí tiene gravedad. Y al tener gravedad se vuelve un elemento clave, además como es dominante, es un elemento clave para formar galaxias. Entonces nosotros desde hace ya más de 20 años hemos emprendido la aventura de entender cómo se forman las galaxias en diferentes contextos, con diferentes propuestas para esa misteriosa materia oscura. Porque la gran pregunta es, ¿qué es esa materia oscura? ¿De qué está hecha? Es 5 o 6 veces más abundante, más numerosa que la materia ordinaria, no obstante hasta el día de hoy no hemos logrado detectarla. Y nosotros entonces hemos empezado a explorar diferentes tipos de partículas elementales que se proponen que son esta materia oscura, partículas elementales que no se han descubierto todavía y hay muchísimos grupos en el mundo a la caza de estas partículas.
Los mecanismos de generación de energía de los cuasares, que son los objetos más lejanos y más brillantes del universo. Y luego hemos visto que estos objetos también existen, aunque sea un poquito en miniatura, en los núcleos de varias galaxias. El mecanismo para generar esta energía es la caída de material, de gas, de estrellas a un gran agujero negro, miles de veces la masa del Sol, millones mejor dicho, en el centro de estos objetos.
El telescopio es simplemente un instrumento que funciona igual que nuestro ojo. Es un instrumento que a través de óptica concentra luz en un lugar y gracias a esa luz podemos entender qué es lo que se está viendo. La diferencia es que nuestro ojo tiene 6-7 milímetros de diámetro y el telescopio puede ser cada vez más grande. Al concentrar más energía de las estrellas en este caso, tú puedes entender mejor la información que te llega, la física de la luz, y con eso pues estudiar, por ejemplo, cómo evoluciona una estrella o cómo se mueve una galaxia lejana. Todo eso es gracias al telescopio. Hay de lentes, hay de espejos. Los primeros tuvieron 8 o 10 centímetros de diámetro. Hoy hay telescopios de 10 metros de diámetro en operación y hay diseños de uno de 40 metros de diámetro y hay telescopios espaciales que se están diseñando actualmente de 10 metros de diámetro, precisamente para evitar la atmósfera de la Tierra que degrada la luz que llega de las estrellas. Nada más por poner un ejemplo, la luz, un fotón que sale hacia la Tierra desde el Sol, tarda 8 minutos en llegar. No hay manera de que sepas que ese fotón empezó su camino antes de que te llegue. No hay manera, es lo más rápido que existe. Bueno, esto que tenemos aquí, lo voy a hacer para que lo vean mejor. Esto es el soporte de una serie de lentes que vamos a poner en el telescopio de 2 metros. Este es simplemente una especie de objetivo, una cámara que va acoplado a un instrumento que es más o menos como de este tamaño, de 1,5 metros por 1,20 metros, que pesa 400 kilos, que va acoplado al telescopio de 2.1 metros del Observatorio Astronómico Nacional en San Pedro Mártir. En este caso, por ejemplo, aquí adentro van 6 lentes, todavía no están puestas, pero van 6 lentes, cada una se tarda, el experto en pulido de lentes, como 6 meses en fabricarla. Luego lleva un recubrimiento, son materiales homogéneos e isotrópicos, esto quiere decir que son de muy buena calidad.
Por fortuna me tocó una revolución en 1968, fue el movimiento estudiantil, era la época del amor y la paz, del comunismo, todos íbamos a tener oportunidades y como cualquier otra persona en cualquier revolución, yo consideré que esa revolución era mi revolución.
Para las mujeres es más difícil todo, porque tienen una carga muy fuerte en las casas. Me da mucho gusto saber que en este momento en la Universidad de México el 51% o el 52% de los estudiantes son mujeres.
Digo, no solo quería ser astrónoma, yo quería casarme, tener hijitos. Y ahí esa doble ocupación, por decirlo de alguna manera, complica mucho las cosas.
Y actualmente, bueno, la fracción de mujeres mexicanas en astronomía profesionales es del orden, si no mal recuerdo, del 30%. Es decir, todavía no es el 50% que quisiéramos, pero eso es alto con relación a otros países como, no sé, por decir, Alemania o Japón, donde las fracciones son mucho menores. Son 5%, 10% nada más de mujeres en astronomía.
Que es más difícil que logren ciertas cosas por la sociedad, no tanto por su capacidad. Eso no tiene nada que ver. Y bueno, en general la astronomía es el ejemplo claro de que muchos de los grandes descubrimientos que se han hecho ha sido por mujeres.
Mi reivindicación actual es el derecho a la muerte digna. Yo he hecho toda mi vida lo que he querido y creo que en el momento en que yo decida que debo morir, debo poder hacerlo con dignidad.
Si no hubiera sido astrónoma, hubiera sido cantante de ópera. Me encanta cantar.
He sido ama de casa, yo hubiera tenido 12 hijitos, que era mi pasión de niña, o hubiera sido ser cirquera, yo de niña quería ser trapecista y subirme a los elefantes.
Quería construir cosas, quería ser biólogo, paleontólogo, arqueólogo, incluso hasta bombero, como todos los niños.
Algún tiempo la hice de periodista, de reportero.
Me gusta cantar, me gusta bailar.
México, tierra de astrónomos.
La astronomía es parte de la cultura. Nosotros necesitamos que en nuestro país la cultura se desarrolle y por lo tanto que se desarrollen todas las ciencias, todas las artes, todas las humanidades